In this video, we'll dive a bit deeper into how quantum computers work. Let's start with how a regular computer represents information. The bit. It can be 1 or 0, which is convenient for representing information via a switch controlling the flow of electricity. 1 and 0 map to on and off. In a quantum computer, the fundamental representation of information is a qubit. A qubit can represent not only a 1 or 0, but a combination of both at the same time. Well, what do we really mean by both? This is a tricky question because this is where our everyday experience doesn't help and the laws of quantum mechanics take over. Quantum mechanics tells us the state of a qubit can be any superposition of a 1 and a 0. What's a superposition? That's a state in which a qubit cannot be purely described as being 1 or 0, but rather some complex combination. Still confused? Fortunately, we can visualize these complex states using a block sphere. Now, instead of a switch with one of two values, we represent the state of a qubit as a point on the surface of a sphere. Different points represent different qubit states, different combinations of 0 and 1. Many of the logic operations used in regular computers can be mapped to rotations of the qubit state on the sphere. For instance, a regular NOT gate, which flips between a 0 and a 1, has a quantum equivalent that rotates qubit state from the North Pole to the South Pole. This can rotate a 0 to a 1 to a 0, and it does the same to any superposition state as well. In our graphical representation, a state on the equator of the sphere is actually an equal superposition of 0 and 1. Move towards the North Pole, and it's a bit more heavily weighted to 0. Move the other way, and it's more heavily weighted to 1. Move around the equator, and something different changes. The phase of the qubit. At different points on the sphere, this leads to superposition changing between 0 plus 1 to 0 minus 1. Changing this is a bit like moving along a wave from peak to trough and back. It's the same wave, just different phases. And now here's something interesting for you. When you measure a qubit in superposition, you get either a 0 or 1. That's it. You can never determine if a qubit was in superposition with one measurement. Instead, you have to perform many measurements. Even if the exact same state is prepared every time, the outcome of each measurement will always be random. The likelihood of measuring 0 or 1 is determined by how much 0 or 1 appears in the superposition, where you are on the sphere. This idea that measurement collapses quantum superpositions has huge impacts on how quantum computers actually function. We build real qubits using all kinds of different hardware, such as tiny loops of superconducting wires, or individual atoms in a trap. We can use two different physical states to form a qubit, and then perform logical operations by blasting the qubits with light, either microwaves or laser light. Tiny pulses timed just right can flip the qubit from one state to another. There's one more element we use in quantum computers: entanglement. This is a special link between quantum systems that can be only described using quantum physics. In a sense, when two objects, like qubits, become entangled, they can't really be described as two objects any longer. They're now one shared object, a condition that can again be induced by applying the right pulse of laser or microwave radiation. There are various ways to represent this visually, as we do in our Q-CTRL products, but it has huge impacts on how adding qubits to a quantum computer increases the overall performance of the system. Next time, we'll introduce how these fundamental resources can be put to work in quantum algorithms. You can learn more about Q-CTRL's quantum firmware and our tools to build error-robust quantum algorithms via our website.